Good morning, students. I hope you had gone through the previous lecture videos in which we had already covered the ray optics portion till the lens maker's formula, and now we are going to start the second part of ray optics, in which we are going to study the refraction through prism, expression for refractive index of prism, dispersion, angular dispersion, and dispersive power, blue color of the sky and red color of the sky and red color of the sun at the time of rising and time of set. And we are moving through to the different optical instruments: compound microscope, astronomical telescope of reflection type and refraction type, and the Newtonian telescope. So resolving power of microscope and telescope will also be covered in this portion. So in this video lecture, we are going to cover the whole prism portion. Okay. So moving on. So as you know that prism is also a refraction object, is basically, but in 10th standard you had already learned that prism is a device, is an instrument which can disperse the light, which can split the light into its constituent visible colors, that is Vibgyor. So this is a schematic structure of a prism which is normally you have seen in the physics laboratories. So there are two refracting surface over it, and this is particularly known as the prism angle A. So when the light, incident light came to any refracting surface, it will refract and go through the other part of refracting surface, and then dispersion is being takes place. So we are going to derive the first refraction formula through a prism. So let us consider a surface ABC, uh, cross-sectional area of any prism, which being taken here is as ABC, of refractive index mu and the prism angle capital A. So when the incident light came through at an angle I, so there are two normals over here. One is normal N1, which is associated with surface AB, and other normal N2 is the normal associated with surface AC. Here I want to quote that AB and AC both are refracting surfaces. So moving on, this is particularly angle I and angle R1, and here is angle R2, and that is angle of emergence E. So in this whole type of structure, if we extend the incident light and we extend the refracted and final emerged light, then we can get a deviation angle. We can determine the angle at what path had been changed of incident light with corresponding to the emergent light. So that angle is called angle of deviation, which is denoted by delta here. So if we go through all these ticks. So here is a angle of deviation delta, this is incident angle I, this is the emergent angle E, it is R1 and R2, and this is the basic whole ray diagram structure for the refraction of light through a prism. Now, in a quadrilateral APOQ, if you go through the quadrilateral APOQ, then you can clearly see that angle A and angle O is combinedly should be equal to 180 degree. And here we also see that angle R1 and angle R2 plus angle O is also equal to 180 degree. So in triangle OPQ also we can see R1 plus R2 plus O, that is equal to 180. By combining these first and second equation, we can get the equation that angle DPQ. Again we can take another triangle, angle triangle DPQ. Then here is delta is basically the exterior angle of angle P and angle Q, which is I minus R1, and this is E minus R2. So we can determine delta equals to I minus R1 plus E minus R2, because in angle DPQ, delta is here is termed as the exterior angle. Now, so delta equals to I plus E minus R1 plus R2. Now you can see that in equation 1, A plus O equal to 180 degree and R1 plus R2 plus O equal to 180 degree. So from equation 1 and 2, we can go through that angle A is equals to R1 plus R2, and if there is somehow for minimum angle of deviation, if that angle R1 is equal to angle R2, in which it is only possible when ray PQ is parallel to BC. So that term is that delta equals to, can be termed as I plus E minus A. So we can write that I plus E is equals to A plus delta. Now the sum of angle of incidence and angle of emergence is equal to the sum of angle of prism and angle of deviation. This is the very important relation which we had derived here. On the basis of this expression, we can determine our further calculative equations for the refraction through light, refraction of light through the prism. So variation of angle of deviation with angle of incidence. This is a very important fact on the basis of which we can determine the formula. So as you see that if we draw the curve of incident angle with respect to a different deviation angle, then we can get this type of curve. So now you can see that as you increase the angle of incidence, as you increase the angle of incidence, the angle of deviation should decrease, and at a certain point, after more increasing the angle of incidence, the delta will be increases. So this particular point is called the angle for minimum deviation. So at this point I is equals to E. So if we calculate the whole equation on the basis of minimum deviation angle delta m, so when angle of incidence increases, the angle of deviation decreases, and at a particular value of incidence, the angle of deviation becomes minimum. So that is called the angle of minimum deviation. So at that time, delta m is I equals to E, and that times R1 equals to R2, that is R. So we can write the previous equations of A equals to R1 plus R2, which will become A equals to 2R, and the equation I plus E equals to A plus delta, which means I equals to E, so it will become 2I equals to A plus delta m by 2, and here we get the angle of incidence I equals to A plus delta m by 2. So now here we get the angle of refraction also and angle of incidence. So it is very easy to write down the refraction formula for the prism, because we know that from Snell's law, refractive index mu equals to nothing but the sine I over sine R. So if it is sin I over sin R, then it will be, according to Snell's law, we can term mu equals to sin I by sin R1, or that is sin I by sin R, and finally we get the formula that is mu equals to sin A plus delta m by 2 by sin A by 2. So this is the formula for refractive index for through any prism, where A is a prism angle and delta m is the minimum angle of deviation. So this is a general formula, but suppose if we are going to consider this formula for any thin prism, in those cases for thin prism we know that the angle should be small, then sin I nearly equals to I and sin R is nearly equals to R. So in that cases mu can be termed as mu equals to A plus delta m by 2 by A by 2. So 2 and 2 will be cancelled, and we get the A times mu equals to A plus delta m, and then minimum deviation angle delta m will be A times mu minus 1. So this particular formula is for thin prism. So if there is being asked in any physical problem that we are going to consider any thin prism, then you can use this kind of formula. Now, you can take the screenshot in the middle of video so that you can make your own notes. I hope that this particular written structure, written documents are quite enough for your notes preparation. So you can take the screenshot in the middle of video. Now, moving on. Now, the refraction by a Snell small angle prism for a small angle of incidence. So that is the same which I had already drawn to you. So if the small angle prism, that is A is small, so obviously the incidence angle and emergence angle will be very small. So in that cases, the every refraction and incidence angle will be small. So in that case, the sin I tends to I and sin R tends to R. So basically you get the similar formula which we had drawn earlier. So that is E by mu R2, and similar we get A plus delta mu A, and delta equals to A times mu minus 1. So this is the refraction through a prism. Now moving on to the next part, that is in which we are going to calculate dispersion for a white light and dispersive power. So the phenomena of splitting a ray of white light into its constituent colors wavelength is called dispersion, and the band of colors from violet to red is called spectrum. But remember that this sort of dispersion and this sort of spectrum is should be considered as a visible spectrum, because we know that in any type of electromagnetic wave, or we can term as a sunlight, so there are more any other radiations is also available. So basically if we pass through any sunlight through a prism, then the spectrum which is seen by eyes, so that spectrum is basically spectrum belongs to visible portion of the light. So that spectrum is video. So cause of dispersion is because the each color have a different velocity and the wavelength. So corresponding to that, the prism material provides the different refractive angle corresponding to different colors, and that's why the refraction of each color is different, and hence we got the phenomena of dispersion. So similarly, so mu, if we consider the mu v for violet, then mu v equals to sin I by sin rv, and mu r equals to sin I by sin rr, where r is stand for red color. So as you see that refractive angle, or we can say the angle of refraction for different color is different, and that's why different type of refractive index will be offered by the prism material to the white light, and that's why dispersion occurs. So in that case, as you see, the mu v is greater than mu r, so the colors are refracted at different angles and hence get separated. Now the dispersion can also be explained on the basis of Cauchy's equation, and it is quite not relatable in your course. So that is now going through the angular dispersion. So the difference in the deviation suffered by two colors in passing through a prism gives the angular dispersion for those colors. As you can see in the diagram, that violet is the most deviated color because it has the very lowest wavelength, and red is the least deviated color because it has the highest wavelength. So the difference between the deviation between violet and red is basically known as the angular dispersion. So now we are going to calculate that thing, that is phi equals to delta V minus delta R. So if we are considered for a thin prism, then delta V is now here is, so delta V can be termed as we know that delta V equals to A times mu v minus 1, and delta for red is A times mu r minus 1. So by taking the difference of these two equations, we get the angular dispersion phi equals to mu v minus mu r times angle of prism, that is capital A. Now we are going to calculate dispersive power. So dispersive power is the dispersive power of any material of prism for any two colors is defined as the ratio of angular dispersion for those two colors to the mean of deviation produced by the prism. So it may also be defined as dispersion per unit deviation, that is omega equals to phi by delta. So where delta is the mean deviation, that is delta V plus delta R by 2, and delta V minus delta R by 2. So the omega is equals to delta V minus delta R by delta omega V minus omega R times A by mu y minus 1 times A. Now here I want to understand you that delta V plus delta R by 2, when we think about the mean deviation, so mean deviation is basically nothing but the deviation of yellow color. Okay, deviation for yellow color, because yellow color is being almost have the middle range of wavelength in the terms of Vibgyor. In the group of Vibgyor, yellow color has the average mean value of wavelength. So that's why we are using the deviation of yellow color here. So this formula can be written as omega equals to phi by delta for yellow color, that is delta V minus delta R by delta for yellow. And as you know, delta V minus delta R we had already calculated, mu V minus mu R times A, and delta for yellow is mu Y minus 1 times A. Now A and A can be cancelled, and finally omega will be mu V minus mu R by mu Y minus 1. So this is the whole point of dispersion, dispersive power for a prism. Let me clear the extra written portion over here. Now, so scattering of light. Now, as you see that sky has the blue color, and at the time of sunset and sunrise, sky appears to be reddish and sun is also appears to reddish. So that is also the reason of the scattering of light. So the molecules of the atmosphere and other particles that are smaller than the longest wavelength of visible light are more effective in scattering light of shorter wavelengths than light of longer wavelength. So the amount of scattering is inversely proportional to the fourth power of wavelength, which is Rayleigh effect, or we can say it is Rayleigh criteria. In other words, we can see, we can understand it easy because the red color has the largest wavelength. So only that sort of color will come to our eyes without suffer any type of deviation which is caused by dust particles present in the atmosphere. While on the other hand, other particles of colors, or we can say other rays of colors will deviate it from the dust particles. So at the time of sunrise and sunset, we can see the reddish sky and the reddish color of sun. Now at the time of scattering of light, for considering as the sky for blue color, so that sky will appear blue at the time of afternoon. If you go through the morning or evening, then you can see the sky at that time is not appearing blue. Blue color of sky will appear most of the time is afternoon. Okay, at the time when sun is at the top of our head, at least making an angle 90 degree with the surface of Earth. At that time, the skies appear to be blue because at that time the scattering of blue color is happening in the atmosphere. So this is the whole reason of appearing sky blue and the reddish color of sunrise at sunset. So till here I will conclude this video and I will wrap up here. In next video lectures we are going to discuss some optical instruments, that is optical instruments related to compound microscope, astronomical telescope and other things. Till then you can continue your study, watch the video and like, share, subscribe the channel. Thank you students, thank you learners.